Okay, scientific method. Scientists, and that includes biologists, geologists, physicists, not just chemists, we have a particular way of approaching learning. And it emphasizes observation and experimentation. We don't just sit around and think of something and philosophize about it. So the ancient Greeks were philosophers, and they sat around and they thought about stuff. But they didn't experiment, okay? And so that's an important difference. The scientific method is not a rigid procedure. It's just a generalized approach. It's not, okay, follow steps A, B, C, D, and you'll get the answer. That would be easy, but it would also be boring. And it's not even possible. So it's just an approach. There are 4 key characteristics to the scientific method. So usually we're going to start with an observation. You notice something happening. I didn't think ahead to create an example. Okay, I used to teach in Tulare, and on my way to Tulare, I would go past these cornfields. And I noticed that the corn was shorter at the edge of the field, and it was taller in the middle of the field. That's an observation. You might say, oh, that's not very exciting. Well, driving to Tulare is not very exciting either. So, you got to do something with your mind. So I observed this. So from an observation, then we have a hypothesis. So my scientific mind wonders, why? Why is the corn taller in the center of the field and shorter on the edge of the field? Don't know why. Hypothesis. So you could come up with several different hypotheses. You could say, well, maybe the irrigation is such that there's not as much water on the edge of the field. Or we could say, well, the edge of the field is next to the roads. Maybe the exhaust fumes from the cars being more concentrated on the edge of the field are stunting the growth of the corn. Those are 2 possible hypotheses. You can have crazy hypotheses. You can say, well, I think the farmer wants it to look like that, and so he comes by in the middle of the night with a hedge trimmers, and he trims it like that. Now, is that very possible? Well, it could happen, but it's not very likely, right? So some hypotheses are reasonable, some are crazy. But it's a hypothesis, and I think this is why I have observed this. From the hypothesis, we generally go to an experiment. A hypothesis isn't any good if we can't test it. So if I wanted to test the hedge trimmers one, I'd maybe just camp out in the field, right, and watch. I might have to do it many nights in a row, and I could establish that no one was coming and trimming the corn, right? There are many ways that you could test the other 2 hypotheses about the water. You could take soil samples and measure the soil water content in various places in the field and see if that's the case, that it's less water at the edges, and that's why it's not as tall. The exhaust fumes one would be a little harder to test, so I'm just going to choose not to talk about that one anymore. So you do this experiment. We'll just stick with the water one. You stick with the water one, and you find out that, no, actually there's actually more water at the edges, because that's, at least at some edges, because that's where the water comes in. So you look and you see, well, there's no correlation between how tall the corn is in this one field and how much water there is in the soil. Well, what does that do to your hypothesis? It says it was wrong, right? So you test the hypothesis with an experiment, and that either confirms your hypothesis, says yes, it's correct, or causes you to either revise or just completely toss out your hypothesis. So you can go around in circles here for decades, actually. Science is a long-term thing for many types of experiments. So you test your hypothesis, and then you revise it, and then you test it again, and you go around and around. Once you've got your hypothesis so that it's standing up to the experiments that you're testing it with, it may become a theory. We also have laws. Actually, let's go, let's go through these slides, getting ahead of myself. So the observation, that's generally something that you can observe. Sometimes you can observe it with your naked eye, like the height of the corn. Sometimes it might require expensive and very sensitive instruments to make that observation. But it usually involves some description or measurement of some aspect of the physical world. Oh yeah, I forgot about this. So there's an example in your textbook. This guy who lived back in the 1700s, Antoine Lavoisier. I'm not going to test you on history, okay, so don't worry about that. He studied combustion by burning substances in closed containers. So many chemists enjoy messing around with fire. We're just like secret pyromaniacs. And how many jobs are there where you can actually play with fire during the course of your job, right? So fire is a fascinating thing to many people. You put a log in the fireplace, you burn it, and then it turns into this white, ashy stuff that blows all over the place, but most of it's gone. What happened to it? So Lavoisier was interested in this. So he put things in closed containers and burned them to see what happened. And what he observed was that the mass of the container and the contents didn't change. We know that if we burn a log in an open fireplace, the mass changes, right? The log was heavy when you put it in, and the ashes are very light after it's done burning. But if you burn something in a closed container, you weigh the container before you burn it, you weigh the container after, it weighs exactly the same. That's an observation. Makes him think, why? What's going on? So from the observation, we get to a hypothesis. A tentative explanation, I think this is what's happening. A good hypothesis is falsifiable. It's possible to prove it wrong. So his hypothesis was that combustion, the burning, involved the combination of a substance with a component of air. So he thought, well, obviously whatever's burning is getting smaller, but he says, I think it's combining with something in the air, and that's why in a closed container the mass doesn't change. It's just changing form. Then we test hypotheses with experiments. Experiments have to be very highly controlled because there's lots of different things that could affect the results, and the more that you can control that, the better your experiment is going to be. We design them to validate or invalidate a hypothesis. So if the experiment shows the hypothesis to be incorrect, we either modify the hypothesis or throw it out again, throw it out entirely. If we revise it, then we test it again. And like I showed you on that other slide, we go around and around and around on that. A number of similar observations can lead to a scientific law. A law is just a brief statement of what happens. It doesn't explain why, but it does predict future results. And it's also subject to experimental testing. So you've heard of the law of gravity, right? So here I have a whiteboard marker, and I'm going to hold it out at shoulder height. And from your experiences with the law of gravity, what's going to happen if I let go of this? It's going to fall, and it's going to go down, right? Yep, every semester. Every semester it does that. It falls to the floor. Does the law of gravity explain why that happens? No. It just says that it will. So that's what a law does. Laws are also subject to testing. I just tested the law of gravity, and sure enough, it's still true. I wouldn't recommend testing the law of gravity by jumping off the building, because it is true, and that's not going to end well. So Lavoisier, from his observations, developed the law of conservation of mass, which says in a chemical reaction, matter is neither created nor destroyed. So from his observations that burning something in a closed container, the mass doesn't change, this was his law, conservation of mass. If we have one or more well-established hypotheses, not the observations, but the hypotheses, this can lead to a scientific theory. A theory is different from a law. A theory is an explanation for the observation or the law. It's a model of how nature is. It is also useful for predicting future behavior, but often predicts well beyond the original observations. And so theories are very, very important. They are also subject to experimental testing. So Lavoisier's law about the law of conservation of mass led to someone else's theory. John Dalton, in the 1800s, based on Lavoisier's law, came up with the atomic theory. So here's a summary of the differences between a law and a theory. The law says what happens. It comes from observations. It can be proved false. A theory tries to explain why things happen. Law is what, theory is why. The theories arise from hypotheses, whereas the law comes from observations. Theories can also be proved false. A theory is as close to truth as science can get. It's not possible to prove something correct in science. You can't prove it to be true. The closest we can come is to say, well, no one's been able to prove it false. And so then, of course, there's always those people that say, well, I'm going to prove it false. And that's what leads to new important discoveries. Okay, conceptual checkpoint. So based on what we've talked about, which statement most resembles a scientific theory? So the first one is, when the pressure on a sample of oxygen gas is increased 10%, the volume of the gas decreases by 10%. So when we're answering this question, this is testing, do you know what a theory is? Does a theory say what happens, or does it explain why? A theory explains why. So does choice A explain why? No. It says what happens, but it doesn't explain. So that's not the answer. So we'll cross that one out. The volume of a gas is inversely proportional to its pressure. If the volume goes up, the pressure goes down. Does that explain? No, it says what happens. So that's also an observation or law. A gas is composed of small particles in constant motion. Is that something that can be observed? Can we observe those small particles? No. No, we can't actually. Does this attempt to explain gases? I realize this is probably not super obvious to you, especially at 8:30 in the morning. This is actually the correct choice. This is most resembling a theory, that a gas is composed of tiny particles in constant motion. This is not saying what happens. This is trying to explain why something is the way it is. And then the last one, a gas sample has a mass of 15.8 grams, a volume of 10.5 liters. That's not trying to explain anything. That's just saying this is what the sample is like, right? That's like saying the bench is black. Is that an explanation? No. Any questions? So atoms are really small. How do we know that they're real? Well, here's a picture of atoms. It's not a very clear picture, but this shows the Japanese kanji characters for atom written with individual iron atoms on top of a copper surface. So the purpley little cone things here are the atoms, and the blue is a smooth copper surface. There's a really cool video that shows how they do this, but I don't think we have time to look at that right now. These images like this cannot be obtained with an optical microscope. They can only be obtained with a scanning tunneling electron microscope, which involves measuring a current and moving a tiny probe. And so these images are generated with a computer. So there's nothing visual. We just use the signals from the computer to generate a picture. But this is direct evidence that there are individual atoms.